Now, let's expand this thought a little bit further. One of the utilities of formal charges is not only that they can show us where the electron poor or electron rich regions are, they can actually help us decide between two or more valid Lewis structures to determine the most stable one. Now, it may seem strange that we could have more than one valid Lewis structure for a species, but it does happen, and we're going to talk about that more when we talk about resonance forms. But I'm going to give you an example here, and we're going to work through the different possibilities for the cyanate ion, and I'm going to show you how you can use the formal charges to determine the most preferred structure. So let's fill in some gaps here. Formal charges can help us decide between two or more valid Lewis structures to determine the most stable one. All right. And in this gap is a very important expression, an important phrase called formal charge separations. Formal charge separations. A formal charge separation is very important. A formal charge separation is when we have an electron-rich area sitting right next to an electron-deficient or poor area in the species. They are generally not stable. So another way of saying that is if you have a positive formal charge sitting right next to a negative formal charge, that's a formal charge separation. And those generally are not energetically stable. Additionally, if you have electron density, then it will generally prefer to sit on the more electronegative atoms. So for example, in the case above, we had an electron-rich region sitting on the more electronegative atom. That is generally preferred. And then one more comment here. When considering our formal charges, the best formal charge is a 0. That's usually the most stable. And if you ever see a +2 or -2, +2s and -2s, they indicate an atom that is so electron poor or so electron rich that it usually gives us an idea that the species overall, either the molecule or the ion, is unstable. So there are three possibilities here for a cyanate ion. So here in our exercise, we have a new ion that we have not yet discussed. This is the cyanate ion. It's not one of the ones that I've asked you to learn, but I'm going to use this as an example to represent what's going on in formal charges. And I'm using the word resonance, and I'll explain more what that means here in a moment. But there are three valid Lewis structures for the cyanate ion. So rather than saying resonance right here, I'm going to say Lewis structures for the cyanate ion, OCN with a minus charge. We're going to draw each one, then assign the formal charges, and based on the formal charges, we're going to answer this question: which one is the most stable based on this information up here? Okay? So I'm going to draw O, C, N. O, C, N. O, C, N. And I'm going to do Lewis structures, and you're going to see when I'm doing this that I'm going to get three possible valid Lewis structures. They're valid structures, following my rules. So remember that oxygen is a valence of 6, carbon is 4, nitrogen is 5. And this is a negative charge overall, so I'm going to add 1. Right? So I've got 16 valence electrons. And by drawing the skeleton right here, I've used 4 of them. So I've got 12 left. The carbon is the less electronegative. It's my central atom. The others are my terminal atoms, so they get the electrons preferentially. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I've used up all of my electrons. So you can see I've used up all of my valence electrons. I don't have any more to distribute on the central atom. And we know that in order to satisfy the central atom, what do? We shift to share. We shift a pair to share. So we're going to form a double bond by shifting one of these lone pairs to share it with carbon. And now you see where the different valid structures come into place. Notice, if I am going to decide that I need to shift a pair of electrons to share it with carbon, I could pull an electron pair from there, from the oxygen, or I could pull it from nitrogen. Well, what if I pulled it from oxygen? Then I would have a double bond there, and these electrons would go away, wouldn't they? But I could have just as easily have pulled it from the nitrogen, couldn't I? And that's how it's going to give us the different structures over here. So let's come back to this. I've pulled an electron pair to share it with carbon. I've shifted a pair to share it. Carbon is still not satisfied, though. So where do I pull the other electrons from? Well, I could pull another pair from nitrogen, or I could pull another pair from oxygen, couldn't I? Let's pull the other pair from oxygen just for now. Okay. Everybody's octet is satisfied, right? And I have a triple bond. Well, let's get back to this situation where I had this situation, and instead of pulling the 2 lone pairs from oxygen, let's imagine that I pulled them from the nitrogen instead. Like that. So I've got a lone pair there, a triple bond. That is a valid Lewis structure. They're both valid structures because they were both legitimately drawn following my rules for how to draw Lewis structures. Well, where does the third option come in? Well, what if I had pulled a pair from nitrogen and a pair from oxygen? Then I would get 2 double bonds, wouldn't I? And it would look like this. So all 3 of these Lewis structures are valid structures. They follow the rules. They all have octets satisfied. Everything is good. Now I need to draw my brackets and the charge, because these are ions, right? Brackets and charge. Brackets and charge. But I'll tell you right now that although all 3 of these structures are valid Lewis structures, one of them is the most stable and is therefore going to more accurately represent the cyanate ion as it actually occurs. How can we tell? Well, formal charges are going to help us. So we're going to calculate the formal charges. Formal charges for oxygen, carbon, nitrogen. Formal charges oxygen, carbon, and nitrogen. And I think at some point we're going to get to be well enough practiced at this that I won't need to write out the math. You'll be able to do it in your head. I'll do the formal charges. I'll write it out for the first three. And then for the others, I'll just talk our way through it, and we'll see how easy it is to get the formal charges. Now we know what we're looking for. So the formal charge for the oxygen in this, in this structure, the oxygen has a valence of 6 minus how many can it currently claim? 1, 2, 3, 4, 5 equals a +1. So this oxygen has a +1 on it. Carbon is a valence of 4 minus how many can it currently claim? 1, 2, 3, 4 equals 0. Formal charge of nitrogen, valence of 5 minus 1, 2, 3, 4, 5, 6, 7. And a -2 is the formal charge on that nitrogen. So right away, there are a couple of things that we can tell that is going to probably be really problematic with this Lewis structure. It is a valid Lewis structure, but let's look at the problems here. We have a -2 formal charge, and as we know, -2s and +2s usually indicate unstable species because they show either an incredible amount of electron deficiency or an incredible amount of electron richness sitting on one atom. Probably not going to happen, or probably not going to be very stable. The other problem here is that we have a positive formal charge on oxygen. Positive formal charges indicate electron poor or electron deficient regions. This oxygen happens to be the most electronegative atom in the whole species. If anybody in this species is going to get the electrons, it's going to be oxygen. But here the formal charge for this structure is showing that it's the most deficient. So for those two reasons, I don't think that this structure, even though it's a valid one, I don't think it's going to be very true in representing the most stable species. Let's go to this next one. Let's calculate the formal charges here. And in this case, I'm not going to do the math, show the math here. I'm just going to talk our way through it, because we can do this after we get more practiced. Formal charge of oxygen is its valence of 6 minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 is a -1. See how easy that is? Formal charge for carbon is its valence of 4 minus 1, 2, 3, 4. 4 minus 4 is 0. Formal charge of nitrogen. Nitrogen is the valence of 5 minus 1, 2, 3, 4, 5 is 0. Now look at this. This looks an awful lot better. We don't have any +2s or -2s. And the one negative showing electron richness is actually sitting on the most electronegative oxygen, or atom, which is oxygen. This one is going to be a whole lot more stable than that one. Moving on, we've got another possible one. Let's do the formal charges here, just to see how it looks. Formal charge of oxygen is valence of 6 minus 1, 2, 3, 4, 5, 6. Formal charge is 0. Formal charge of this carbon, valence of 4 minus 1, 2, 3, 4 is 0. And formal charge of nitrogen is valence of 5 minus 1, 2, 3, 4, 5, 6 minus 1. Okay. Now this is not bad. It's got zeros and a -1. That's not bad. But notice when we compare these two structures, this one has the negative formal charge. That is the electron richness on the nitrogen, whereas this one has it on the oxygen. Oxygen is more electronegative than nitrogen, so of the two, the oxygen is the one that more wants the electron density on it. So probably this is the Lewis structure that is the most stable of these three. This is a little bit less stable, and boy, that is just terrible. Not going to happen at all. So we've been able to use our formal charges to choose the best of three valid Lewis structures based on the predicted stability of the species.